Okay, so everyone, we are going to understand the force acting on a current carrying conductor in a magnetic field. Okay, when that current carrying conductor placed in magnetic field of any strong magnet, then how the force is acting on that we have to understand in this activity. Okay, so in this activity we have to arrange the instrument in such a way that you can see here we have the horseshoe magnet. Here we have that current carrying conductor. Here we have this is the current carrying conductor. Okay. And we have attached that current carrying conductor with the external source of electricity as you can see here. Here we have the positive terminal and here we have negative terminal of the battery. Here we have the key and here we again require the rheostat so that we can like control the amount of current flowing through the circuit. Okay, now first we have changed the we have started the key and current is flowing in this particular direction. Okay, let current is flowing in that particular direction here. Okay, that I represent the direction of flow of current. Okay, and that arrow together they represent the direction of flow of current. So when the direction of flow of current is in upward direction like this, okay, then that current carrying conductor attracts toward the north pole. Okay, it attracts toward the north pole. It shows that it acts force on that. Okay, so see here we have that activity we have to understand here. Okay, and we know that the direction of magnetic field is totally depends on the direction of flow of current. Is it everyone? So whenever a current is not flowing through the circuit, that wire, that current carrying conductor remains at position A only. Okay, so this is the position A. It is not showing any deflection when current is not flowing through the conductor then. Okay, now next, but when the current flows from top to bottom, okay, the wire bends and comes into the position C here. Okay, so when current is flowing from top to bottom means like this, in this direction from top to bottom, then that wire moves toward the point C. That means it is attracting toward the point C, and that point C is towards the south pole. Okay, in this particular direction, that wire is bending toward the south pole. Next, if the current flows in a direction, it is reversed. Okay, if we will reverse the direction of flow of current, okay, then the bottom, that means the direction of flow of current will be from bottom to top. That will be from bottom to top, and then the wire bends toward the position B. That time wire bends toward the position like this. Okay, it was a straight, but now when current flowing through the circuit, okay, and its direction is changed, then it is bending toward the that particular side of the magnet. Okay, means toward the north pole. Okay, so that wire sometime it is bending toward the south pole and sometime it is north pole when we used to change the direction of flow of current. So it shows that it is bending toward the opposite pole of the horseshoe magnet. That means it acts the force on it. Okay, and this means that the direction of the force on the wire is perpendicular, which is acting perpendicular to the both of the magnetic field and the direction. Okay, direction of the flow of current. Here the direction of magnetic field is from north to south. Okay, inside the magnet the direction of, and see here we have suppose north pole and here we have south pole. So outside the magnet, the magnetic force of line acting from north to south pole like this, outside the magnet like this. Is it everyone? But inside the magnet it is south to north. Okay. In this experiment, it is noted that whenever the current flows through the conductor, in the presence of magnetic field, a force is exerted on the conductor. So whenever the current is flowing through the circuit, then it bends or it moves away from the magnetic field of the permanent bar magnet or horseshoe magnet. It shows that the force is acting on that conductor. Due to that force, it is changing its position. Okay, everyone? If the direction of current is reverse, we have reversed the direction of flow of current, the direction of force also get reversed. If the magnet is kept reverse, that means the south pole is brought in the position of the north pole and north pole brought into the position of the south pole. What will happen? So if we will change the direction of flow of current or the direction of magnetic field, the deflection will take place. Any one of them, either direction of flow of current or the direction of magnetic field will change. Magnet will change, the magnetic field also change. The deflection of that force acting on that wire will also change. Is it everyone?
I have a doubt, sir.
Yes, beta.
Sir, here we are using the material of any metal, right? Which
Yes,
has
yes, metal wire.
non-magnetic
Yes,
properties
yes,
before. If I put a
yes.
magnet in the place of that bar, so what will happen?
Will you please
Will
repeat?
it show?
Oh. Then see here that wire we have connected with that particular uh, conductor, the flow of current. Here we have that battery is a source of current, right? And when current is flowing through that wire acting as a magnet, electromagnet.
Yes, sir.
Yeah, so if we will place magnet here, we'll also show the same deflection, because here that wire is acting as a magnet. Okay, because we know that, suppose here we have one bar magnet, here we have north and here we have south. So we know that south pole and south pole, or north pole and north pole, or we can say like poles repel each other, repels each other, and unlike poles attracts each other. Is it? So due to repulsion or attraction force, they show the deflection. So the same effect we will observe when we will place magnet instead of current carrying conductor. Same force will going to act on it. Okay, everyone? Understood?
Yes.
Yes.
Yes, sir.
So now we have to understand here the Fleming's left hand rule. First, I want everyone have to take a screenshot for that. Wait a second, I'm just fitting the screen.